let's go ahead and take a look at the classwork together. And page 368, number 1. What is the name for a single possible result? Josh?
Outcome.
An outcome is what we'd be looking for in a particular event. What is the name for the likelihood of an event occurring, Lana?
Probability.
Good. Number 3, that was probability. Number 3, what is the probability of an event that is certain to occur? 1 or 100%, right? If it's certain to occur, if it's definitely going to happen, then it's 100% probability. Right? Does that make sense now, though? Yeah. Right? Number 4, every probability will be between what two values? Josh? 0 and 1, or 0% and 100%, right? Something that cannot possibly occur would be 0, and that which must occur would be 1. What is the probability notation for the following situation? The probability of randomly choosing a pair of sandals. Again, what is the notation going to be here, Lana?
P parentheses sandals.
P parentheses sandals. They focus a lot more on notation and terminology than I do, but whatever. More power to them. All right, number 6. Getting into some real stuff now. Each of the 6 letters of the word bubble is written on a separate piece of paper then placed into a hat. One letter is drawn randomly from the hat. What is the probability of drawing a B? Scott?
1 to 2.
1 to 2. Good. 50% probability, because there are 3 B's and 6 total slips of paper. 3 of the 6 say B, so 3 to 6 which reduces to 1 to 2. What about the probability of a letter other than B? Josh?
1 to 2.
Also 1 to 2, because the other 3 slips of paper. By the way, probability of not drawing a B. Anytime you have the probability of something like a B not happening, we refer to that class as the complement. And very simply, you take 1, which is certainty, minus the probability of something actually happening, 1 to 2. It would leave you with the other 1 to 2, which is the probability of not happening. What about the probability of a vowel, Lana?
I bet 2 is 1/3.
Good, 1 to 3, which would be a 33% approximately probability. There are 2 vowels, a U and an E in the word bubble. 2 out of 6 slips of paper would be a 1 to 3 probability. Number 7, the spinner on the right is spun once. What is the probability of spinning a 4, Scott?
1 to 5.
Good, there is only 1 space that says 4 out of 5 total spaces, so that's 1 to 5. What's the probability of spinning a green area? Josh?
3 to 5.
3 to 5, good. What about a number other than 2, Lana?
4 to 5.
4 to 5. Probability of a 2 would be 1 to 5, so the probability of not 2, or the complement, would be 4 to 5. And the probability of an odd number, Scott?
3 to 5.
3 to 5. Questions on that? Number 8, a middle school has 75 students with 20 6th graders, 30 7th graders, and 25 8th graders. This is probably a small Christian school, middle school. The school principal will randomly choose a student from the middle school to serve as a library assistant. What is the probability of, and they go through some choices. Well, a 6th grader being chosen. What would that probability be, Lana?
4 to 15.
4 to 15. That's 20 to 75 reduced. By the way, we would refer to the 75 class as our sample size, right? The total sample size would be the 75 students. The desired outcome would be the 20 students. The probability or the likelihood would be the 4 to 15. What about a 7th grader being chosen, Scott?
2 to 5.
2 to 5. That's 30 to 75. And then what about an 8th grader being chosen, Joshua?
1 to 3.
1 to 3, 25 to 75 reduces to 1 to 3. Number 9, the senior class of Crystal River Christian School has 46 seniors. This class includes 17 boys and 29 girls. A local Christian radio station will randomly select 1 senior to interview. I will say, from somebody who's in the know, if they were to randomly select, it wouldn't be randomly selected. The school would help them select. But anyway, if it truly were randomly selected, senior from the school, what is the probability of selecting a girl, Lana?
29 to 46.
29 to 46. What about the probability of selecting a boy, Scott?
17 to 46.
17 to 46. What's the probability that the person they select ends up being the valedictorian? Josh?
1 to 46.
1 to 46. If there's only 1 valedictorian of the class, then that would be a 1 to 46. Questions on those?
Was a number 8, letter B, 2 to 5?
2 to 5 was what we said, yes. All right, number 10. Determine whether or not this is valid. The probabilities of receiving each of the 3 colors in a gumball machine are a 2 to 3 chance of red, 1 to 3 chance of blue, and 2 to 3 chance of yellow. Class?
Not
No.
valid.
Why not?
Because
it
they
adds
don't
up
add
to
up
more
to
than one.
Yeah, they'd add up to more than 1, right? That can't be. What about the probability of a number being spun, or the next number being spun and being a 4 is a probability of 3 to 2?
Not valid.
No, also not valid because that probability is
Over.
over 1, right? It's like the poster I had up earlier in the year that said 8 out of every 5 students is math illiterate. 8 out of every 5, wait a second. If you see nothing wrong with the poster, you're one of them. But anyway, yeah, no, you can't have 8 out of 5. Anyway, the probabilities for getting each of the 3 possible letters on the next draw are 43% chance of an A, 9% chance of a B, and 48% chance of a C.
Valid.
Sure, they're all between 0 and 1. They add up to 100%, so that would certainly be a valid set of probabilities. Number 13, the probability of snow tomorrow is 120%.
Not valid.
Well, obviously we're in Georgia, but like what if we were in Alaska?
Mm.
Still not valid because you can't have a probability over 100% or over 1. Questions at all on that classwork? All right, go and turn the page. And as we talk about probability, we want to talk about this concept called counting. You see that term at the top of page 370. Go and write this definition down for counting. Counting is simply determining the number of possible combinations, of various items. Counting refers to not 1, 2, 3, 4 necessarily. It refers to determining the possible number of various items. Possible combinations, of various items. There are different ways in which counting can occur, but you understand that as you determine the total number of possibilities, you're determining the sample size for a probability. So probability and counting certainly go hand in hand. One way of determining a total number of situations possible would be to make lists. I hate this option. But you need to understand how it would work. Let's suppose we've got this guy named Kevin who has a deli, and we see there he's got just a few options, okay? So don't go to him if you want lots of choices, go to Subway, right? Eat fresh, have it your way, whatever the saying is. You go to his place, you can either get wheat bread or rye bread. That's it, okay? Now, you can get one of 3 meats, roast beef, turkey, and ham. You like salami, you like pastrami, too bad, we ain't got it, all right? And then if you want cheese, I have to admire his cheese choices. American, which is boring, sorry. Provolone, a little bit more interesting, especially if the smoke flavor's there. And Munster, which is my personal favorite. Coated in the paprika, it's a little bit of a softer cheese, a rich flavor, excellent choice. But anyway, I do like the cheese choices there. I'm a big Munster fan. I'd never heard of it until I was I think it was in junior high, and I worked for a guy who was one of my dad's friends, and he had some gardening he needed to get done, and I needed to make some money. So he hired me to help him with some gardening, and we sat down to have lunch, and he asked if I'd ever had Munster cheese before. I never had, so I tried some. I was like, man, this is really good cheese. So anyway, if you're I don't know if you like cheese I like cheese on a meat sandwich, but anyway, Munster, try it sometime. But anyway, what they did to make this list was they just chose letters. So W stands for wheat, R stands for rye, okay? And then B for beef, not R for roast beef, because they'd already used R for rye. T for turkey, H for ham, A for American, P for provolone, M for Munster. And they make a great big list. Well, with wheat, you could have wheat with roast beef. You could have wheat with turkey. You could have wheat with ham. Well, if you do wheat with beef, that could be wheat with beef in American. That would be wheat with beef in provolone, wheat with beef in Munster. And it just keeps building and building. And eventually, if you look there are 18 different possibilities listed out. They color-coded. All the wheat options are blue, and all the rye options are green. That's a very rough way of putting together a counting scenario. But you could use a list. Option number 2 is a tree diagram. This is somewhat more fun only because you get to break it down a little bit more easily in slightly picture format, a little bit, okay? Just take your wheat, and when you start with wheat, 3 meats. But each meat could have 3 different cheeses. And suddenly you notice there are now a total of, count them down, 9 options for meat and cheese on wheat. Then you do the same thing for rye. Beef, turkey, ham. Each one has 3 cheeses. Look at that, 9 more options. Look at that, total of 18 possibilities. Also not real fun. And then there's the counting principle that you see on page 371. You say there are 2 choices of bread. There are 3 choices of meat. There are 3 choices of cheese. And here's the key. They build one upon the other. Well, you simply multiply. And lo and behold, how many choices we got? Isn't that a whole lot faster than tree diagrams and making lists and stuff? I am a big fan of not making lists or tree diagrams, though sometimes they can be helpful. But for the most part, this is the way I'd like to do it. Make sense? Just multiply all your things together. Look at the example there on page 371, the example problem 8.2a. It says, how many possible outfits could Michelle make if she has 5 different skirts, 6 blouses, and 4 pairs of shoes? Now, Rhonda, this assumes they actually all match. Okay, you know you can't just put any skirt with just any blouse, right? Okay, some things just don't go together. But somehow, all of them all kind of match or coordinate, okay? How many possible outfits could she make? Well, you just multiply. 5 times 6 times 4, and there are 120 possible outfits. If they all matched, she could literally go the entire year and only wear the same thing about 3 times. Yeah. Anyway, do you see how easy that is? The fundamental counting principle. You multiply all the possibilities in one set times all the possibilities in the next set, and so forth. Now, we could add on further. Let's suppose this Kevin guy decided, my options aren't enough. Let's go ahead and offer toppings as well. Now, again, it's kind of weird, but you could have either pickles or lettuce or tomato. Why or and not and? I don't know. It's kind of like those commercials for bed or breakfast instead of bed and breakfast. Sweet or sour chicken instead of sweet and sour chicken, you know? So the guy's like, the guy comes down for breakfast, and of course he doesn't get it because he chose bed. And everyone's out there in the main area, the eating area, all sleeping on the tables. It's like, glad we picked bed. Let's go to the restaurant and get something to eat. You know, all the people picked breakfast. They didn't pick bed, so all they got was breakfast. Or, you know, the guy's like, oh, you like your sour chicken? You know, it's like, oh, it's so bad. We need sweet and sour chicken. Sometimes and is good. But anyway, in this example, because it helps the example a little bit better, you just added 3 toppings. Well, guess what? You've now made it so there are 54 possible combinations of sandwich you could have, okay? Now, if you give the and, that makes even more, but we're not ready for that just yet. Just kind of showing an example of how that could be. The question might be, though, how many different sandwiches could include lettuce, for instance? Well, lettuce is one of 3 toppings, right? So lettuce could go on any one of these other 3, right? You could have, the wheat with the ham with the lettuce. So how many could have lettuce? Well, 3 of the 54, 3 of the different 54 could. So you can kind of break it down that way as well. But, as far as figuring out how many total sandwiches could you have? You could have 54 different sandwiches. Turn the page. Now, if there is a successive pattern, in some cases, it's easier to use the tree diagram. Look at the next example problem. In 3 flips of a fair coin, meaning not one of those ones with 2 heads on it. You ever see one of those trick coins? It's like heads on both sides. Yeah. All right, heads I win, tails you lose. You don't even have to do that. It's just like, all right, if it's heads I win, if it's tails you win. All right, let's flip the coin. Hey, what do you know? It's heads. Let me examine that coin. Hey. Anyway, always examine it before they flip it. But anyway, it's a regular coin, a fair coin. What's the probability 2 of the flips would land heads up? Couple ways to do it. The way that they show it here, you see that they take the first flip, and it's either going to be heads or tails. Now, after that, you flip again. And if it was heads the first time, it could be either heads or tails the second time. Well, if it's tails the first time, it could be either heads or tails the second time. So we're now up to 4 possibilities. Then you flip it again. Well, again, you could have heads or tails on that heads, or it could be heads, tails, and then a heads, tails. Or they could be tails, heads, and then a heads, you get the idea. And you see they've kind of listed it out there with 2 heads being in red. Again, I don't really like drawing diagrams, so here's the way I would look at it. How many different times could you flip a heads? Well, how many times are you flipping the coin? 3. So there are 3 chances to get heads, correct? Now, Each time you flip the coin, there's how many outcomes could exist? 2. So the first time you flip it, there's 2 things. It could be heads or tails. The next time you flip it, you could get heads or tails. The next time you could flip it, you could get heads or tails. How many different outcomes are possible?
See.
I know you're multiplying. 2 times 2 times 2. 8.
Yeah.
8 total possibilities. I think this is better, but you have to realize there were 3 different times you could have gotten a heads. There are 8 total possibilities just by the counting principle. That's a faster way in my mind to get 3 out of 8. Does that make sense? Okay. So let's look at some examples, some problems here together. On page 372, it says number 1. Actually, you go ahead and read it for us if you would. Scott?
Practice?
Yeah.
The final 2 performances in a concert will include brass performance and string performance. The brass performance will be either a solo, duet, or trio. The string performance will be either harp or violin.
And we're trying to figure out how many total things could be here. Now, they tell you to use the whole list thing. I don't do list thing, okay? I'm lazy, okay? I admit it. I've admitted it all year. I'm not going to stop admitting it now. How many different types of brass performances could there be, class? 3. Following the brass performance, there's going to be some kind of string performance. But how many different kind of string performances could you have? 2. How many different ways could they put together the concert then? 6. There are 6 different ways that the concert could happen. That's a lot faster in my mind than saying solo, duet, trio, and it could be solo with violin or it could be solo with harp. It could be duet with violin or duet with harp. It could be trio with violin or trio with harp. Hey, look, 6 chances. 3 times 2 is 6. Big fan of the numbers, okay? But that's what they were going for with the whole listing. The next one's interesting. There are 3 marbles in a bag. 1 red, 1 green, 1 blue. John will randomly draw a marble 3 times, replacing it each time. So he reaches in the bag, pulls out a marble. How many possibilities exist the first time he reaches in? 3. Then he puts it back in. So he could draw the same marble again, couldn't he? All right? He reaches in, rattles them around a little bit, pulls out a marble. How many marbles were there in there? 3. So there were 3 possibilities the next draw. Okay? Then he's going to reach in again after putting the marble back. Reach in, pull out a marble again. How many chances are there?
3.
How many different ways could he draw marbles out? 27 different ways he could draw a marble. He could draw red, then red, then red again. Now, probably you suspect him of not actually releasing the marble when he reaches back in. That's like, yeah, I don't even think that would fool Chloe. I'm going to randomly draw a marble. It is a red one. All of you look. Now, what are the chances I draw it again? Voila! Another red one. Chloe would be like, you just didn't drop it, Daddy. Like, even a 6-year-old could figure that one out. But, if theoretically, the odds would be 1 in 27 you'd actually do red, red, red all in a row, because there's 27 different ways you could draw it. It could be a red, then a green, then a blue. It could be a red, a blue, and a green. A whole different ways you could do it, but 27 would be our answer there. Look at the next one. Now, this one I kind of misread here. How many different ways could the family be arranged is kind of the way it's looking at. For instance, I come from a girl, boy, girl family. I have an older sister and a younger sister, and I'm in the middle. My wife also comes from a girl, boy, girl family. My family now has girl, boy, boy. Okay, so we're just very symmetric about this. Scott, your family has, let's see, girl, boy, boy. Something like that, right? So there's all different ways in which a family could be arranged. Well, the Larson family says has 3 children. Infant, kindergartner, teenager. And obviously, we believe science here. Each child is either a boy or a girl, okay? So the question is, how many different ways, like girl, boy, girl, boy, how many different ways could their children have been born as far as their gender? Well, the first kid is either, so that's how many possibilities? 2. Then the next kid is also another boy or girl, so another 2. And the next kid is a boy or girl, so another 2. So how many different ways could the family have had their children gender-wise? 8 different ways in which they could have been arranged. Does that make sense? Look at the next example. Mr. Wise needs to buy fertilizer mulch for his yard. He can choose from fertilizer types A, B, and C. So there's 3 different types of fertilizer. Maybe it's like the straw type stuff. Maybe it's the just the chopped up stuff, or maybe it's the pine bark type stuff, whatever. Okay, so 3 different types of fertilizer. And each type of fertilizer comes in 3 colors. He could either get red, he could get brown, or he could get green. I've never seen green. I've seen red, brown, and black as the main fertilizer colors, but whatever. How many different types of fertilizer could he buy? Well, how many brands?
3.
Okay, and how many colors for each brand?
3.
3. So, how many different kinds of fertilizer are there?
9.
9. Seem pretty easy?
Oh.
We get the hang of this? Without the list and without the whole diagram thing, because I'm lazy and don't want to do the diagram thing. Okay. All right, let's keep going. Number 5. 3 6-sided number cubes are rolled. One's red, one's white, one's black. Maybe this is a game where, I don't know, for instance, how many played Risk before? Okay, and there's different colors of dice in Risk, like red is for the attacking and white's for the, okay. Anyway, so maybe that's something like what we've got here, and then black is for the ally to help out. I don't know, whatever. But 3 different number cubes are rolled. You understand, getting a red 1, black 2, and white 3 is not the same as red 3, white 2, and black 1. Okay, those are different from each other. How many different possibilities could you get if you rolled those 3 dice at random?
Wait, no. 54. Wait, what?
How many numbers are on a die?
6.
6. So that first die could be 6 different things, right? The next die could also be 6 different things. And the next die could also be 6 different things. So, how many different ways could those 3 dice be rolled? 216 different ways. 216 different ways. So theoretically then, you would have to roll the dice 216 times before you get the same roll again. Okay, kind of random there. Okay, number 6. Each of Mark's last 4 test grades was either an A, B, or a C. So if we were trying to predict his test, I think he will make a C, then he'll make a B, then he'll make another B, and then finally he'll improve to an A. Or there may be some logic to that, particularly if he's starting off struggling. But if we were trying to predict the order of his grades on those 4 tests, how many different ways could, assuming he passed them all, could he score on these tests?
12? Wait.
Well, he could make 3 different grades on the first test. Then he could make 3 different grades on the next test. Then he could make 3 different grades on the next test. And then 3 different grades on the 4th test. 81. 3 times 3 times 3 times 3. There are 81 different ways in which he could score. Because you understand, if he makes an A, then another A, then a B, and then an A, that's different from making an A, B, and an A, and an A. You see that? These are different orders of tests. If you get test 1, A, test 2, A, B, so these are different from each other. So yeah, 81 different ways in which you could make scores on these tests. Let's go with another one. Number 7. Sebastian. That's a great name. I actually knew a Sebastian. Sebastian is in the market for a new push lawnmower. There are 6 brand choices. The mower could either be gas, electric, or battery powered in each of these 6 brands. And each brand and each model could be either 18-inch, 21-inch, or 22-inch wide deck. How many different lawnmowers could he buy? This one's a little more straightforward, unlike the last few. There are 6 different brands, 3 different powering mechanisms, though I don't know why you'd want an electric lawnmower. If you run over that extension cord and zap fry yourself, it's just not worth it. Or battery powered. Okay, that makes a little bit more sense, though. Give me a gas lawnmower any day. An 18-inch little baby, 21-inch standard, or 22-inch extra wide, which 1 extra inch doesn't sound like much, but What do we got? All right, we got 6 brands, right?
Yeah.
And in each brand, we have 3 different powering methods, and we have 3 different sizes.
Yeah. Is that simple?
It's that simple.
We're complicated that.
I told you, this one's a little...
too.
I told you, this one's a lot more straightforward than the last ones. So, 54. There are 54 different types of lawnmowers he could buy. 54 different types of lawnmowers. All right, number 8. This one's also a little bit more straightforward. Christine needs a new cell phone. She can choose from 3 different brands. Let's just say Apple, Samsung.
Android.
Well, Android is a system that powers it. Apple, Samsung, those are the 2 you see all the time. Maybe LG. I have an LG. Let's go with that. All right. Then the phone colors she likes are silver, black, red, and pink. So she wants one of these 3 brands. She doesn't care which one. In one of these 4 colors, and she has to decide between 3 different phone networks. I guess that would be what, Verizon, AT&T, and T-Mobile, okay? And she wants to insure her phone, and there's 2 different insurance options. How many different ways could she put together her phone package? That was quick, good. You were ignoring what I was talking about and just working the problem. Not sure if I'm thrilled with that.
Yeah, I was just...
Did you get 72?
72.
Yep, 72 different ways to put together the phone package. 3 times, 4 times, 2 times 3.
Wait, where'd you get the 4 from?
There were 4 different colors.
Yeah.
Silver, black, red, and pink. So there's 3 phones, times 4 colors, times 2 network or insurance options, times 3 network options. Gives you the 72. All right, number 9. Here's another one for you. You can't answer early on this one. All right, a travel agency is having a sale on 2 different cruise destinations. You can go to the Caribbean or you can go to Alaska. I don't know why people like to go to Alaska, but they do. All right, customers, I've never been, so I don't know what the hype is about. It just sounds cold. All right, customers can choose from 4 types of rooms, 2 meal plans, and 3 souvenir packages. I would choose I don't care about souvenirs. I just want to eat really well, feel really comfortable, and enjoy the view.
That's what it's all about.
I could care less about souvenirs, but I'm weird. Some people love souvenirs. All right, how many different options can they choose from this travel agency? You got it?
48.
48, good. All right, number 10. Ronaldo's college schedule needs to include 1 of each type of class. There are 2 different English classes, he has to choose 1. There are 4 science classes, he must choose 1. 2 math classes, he has to choose 1. 4 PE classes, he must choose 1. And 3 history classes. How many different ways could he put together his schedule, assuming he can put them in whatever hours he wants? Which isn't always true. Well, freshman year, it's almost true.
192?
Show off. Good, 192 different ways he could put together his college schedule for that semester. Questions on that one? Let's drop down to number 11. Says, for problem 2, what's the probability John did not draw any reds on his 3 draws? What's the probability he didn't draw any reds on the 3 draws? Now for this, I kind of feel like we may want to use one of those diagram things, okay?
Yeah.
So going back to problem 2, remember we've got the 3 marbles in the bag, right? And so he's got red, he's got blue, he's got green. And on his first draw, he could draw any one of these 3, correct? On the next draw, there's red, there's blue, there's green, right? For each of these, red, blue, green, red, blue, green. And then, for each of these, on the next draw, and that's where we came up with 27 total possibilities, remember? We did it mathematically, we said 3, 3, and 3. But what's the odds there are no reds at all? Well, that means this couldn't be a red, this couldn't be a red, this couldn't be a red, no red there, 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 and no red there. But really that actually wipes out all of these options here, which really wipes out all of these options here. So how many options are left without any red whatsoever?
4.
Hold on. 1, 2, 3, 4, 5, 6, 7, 8.
Oh, 8, yeah.
There are 8 out of 27, and honestly, for that one, you kind of need the picture, I think, to visualize this. There are 8 times, because you can't start with red, right? So if you start with red, that shoots everything. So there go 9 of your possibilities gone. If you start with blue, but then you get red on the next one, well, that knocks out those 3 possibilities, gone. And if you draw green and then you follow with red, that knocks out 3 more of the possibilities. But if you go blue-blue, you could still get a red, so that knocks out 1. Or blue-green, you could still get red, that knocks out 1. You could go green-blue, but not red on the next one. Green-green, but you can't have red on the next one. Again, I think the picture is the easiest way to kind of set that one up. So there are times, as I mentioned before, that sometimes it's easier to use that, especially for probability of something not happening. Let's do something similar here on number 12. From problem 3, what's the probability we get girl, girl, girl? What's the probability we get girl, girl, girl? Let's think of it this way. They're about to have a baby, and their very first baby's about to be born. We know it's either going to be a boy or a girl, right? Now, they're about to have a second kid. And if they already have a boy, their second kid can either be a boy or girl. If they have a girl first, their second kid would either be a boy or a girl. But the point is there are now 4 different ways in which their two kids could be born. It could either be boy, 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 girl, girl, boy, girl, girl, right? Then they're going to have kid number 3. And of course, you know how it goes. Each one's either going to be boy, girl, boy, girl, boy, girl, boy, girl, right? But what's the chances it goes girl, then girl, then girl? We know there's 8 total possibilities. But how many of them are girl, then girl, then girl?
3. No. Yeah, 3.
1 chance.
Alright.
Right? This represents 1 possibility. 7, any of these other options would have been different, right? So there's only 1 chance of getting girl, girl, girl out of 8, which makes sense because if you're going to have 8 total possibilities, you could get a girl in the first one, then you'd have to get a girl in the next one, then another girl in the next one. That'd be 3 girls in a row. That's only 1 of the 8 ways in which the kids could be born in the family. Now, then we could get into the genetics of it, the chromosomes and all of that, and we don't, that really messes with the math. Questions on that? Probability is kind of a fun, interesting way of looking at things, isn't it? All right. Well, we will finish looking at this more tomorrow. Your homework this evening. Homework this evening is going to be to do page 374 to 375. Pages 374 to 375. Homework. Numbers 1 through 15, but you can skip number 14. Number 14 is a graphing concept. Obviously, we skipped chapter 7. So pages 374 to 375, the homework, numbers 1 through 15, but skip number 14. All right, we'll take a look at this more tomorrow, and you are dismissed.